Could you see my screen? Everything is okay?
Yes, I can see it.
Okay, so I just want to test. Yes, it works. I have a strange green rectangle on my screen, but I don't know if you have. Okay, so that's true that we would like to present these activities that we have in our teams about working on whole documents. This work is a joint work with Van Linley, Cecilia Ostertag, Antoine Piron, and Mantou Vu, who are PhD students in our team. Why working on whole documents? To be able to recover their ownership of their history, a lot of countries and their government are interested to promote research works to capitalize knowledge about a piece of history contained in the whole document. All documents are often widespread through the world, and so thanks to their digitization, to access to them without needs of traveling and of authorization to access or something like that. New huge databases of all document images publicly accessible and everywhere around the world. But I'm afraid to tell that the tools necessary to use to classify with classified and sorted data are missing. And really, this kind of tools are waiting by the historian and papyrologist in our case, because we work first on papyri collection. You know that Egypt has a fabulous history and a lot of documents access to this history. To work on this kind of document, collaboration between scientists are essential. And the problem is that exchange documents could be impossible for a lot of different reasons, because of the size of the document, because of bad state of this document, or for any political or cultural reasons. Moreover, we have to point out that, for example, in Egypt, a lot of documents are outside Egypt, and they are widespread, and the difficulty for a lot of countries is to access again to these documents that are important for them, but not in their place. This nice papyrus is something that you can see at the Met in New York City. I took a picture when I went, and it's very nice, but this kind of document have been already studied, and they don't need nothing. All the translation have been made and are accessible. It is not exactly our purpose. Our purpose for the first project have been to work on a funeral mask. What it is. Some papyrologists have opened a project, the Geshem project, about studying the Juke collection, which is composed by a funeral mask and what we call cartonnage. What is a cartonnage? Is a kind of box where they put the funeral mask when they unpack mummies. So in the left part, you can see, I don't know if you can see my pointer, you can see the funeral mask as you can find in the when you open mummies. But what you can see in the right part is that if you take off the painting, you can see that the papyrus that have been, the materials that have been used to make the funeral mask is in fact some piece of papyrus that have been whitened previously. So in fact, papyrus is a very costly material, and after using it, they use again to pack mummies when they don't need the text that they have written before. And so some information about economic activities or something like that are stored in this papyrus, and they are interesting thing for the papyrologist. It is not at all literature, poetry, or something like that. Not very, very important texts that are stored in a prestigious museum, but they are very, very interesting when you wanted to study the society in the old time in Egypt. Another material that exists and we work on also is ostraca. In the same period, they can use also not only they use not only papyrus but also shards of pottery. When the pottery are broken, you can use pieces of them to write some not really important thing, like that you wanted to pay something to a soldier, you want to exchange some food with another one. And so it is a way to notice something that can be used for school also when the student need to exercise themselves. So they use shard when they are broken from the original pottery, but after being written, they can be broken again. So the question is how to assemble again, to make the reassembly of this ostraca or papyrus. So before to be able to reread the documents, we have to reassemble. Is it a puzzle task? This is a puzzle task. You can see this nice video, but I can't read it in, I have not taken the risk. I have not taken the risk to run the video inside the presentation, but it is a nice presentation in the web. You can see the address where you see that from a set of pieces, an algorithm is able to present again the original image by organized in the right way all the pieces. But what you can see is that all the pieces here are in fact pretty similar in their shape and they are well cut. You have a lot of different color, which is not at all our case. Why? Because whole documents are many in bad state. You have seen just before. Papyri can be unraveled, and ostraca can be broken after their using. More, the papyri coming from different cartonnage have been cut and used separately to pack mummies in their funeral ornament. So the color can be changed through the times independently, even if the two fragments come from the same original papyrus. So what we can do? First, we can try to group fragments to create classes of potential entities. We turn to Siamese network. What is a Siamese network? A Siamese network is a classical neural network with two branches identical. You can mainly it is a convolutional network, and the specialty is to share weight through the two branches. It has been defined previously both for identification and comparison of signature for the bank account and of fingerprint also. So you present one fingerprint and you compare if it is the same as another one. For the signature, it is the same. How it works. The goal for a Siamese network is to compute the distance or a similarity, it depends how you consider, between a pair of two different inputs. Each branch has a convolutional neural network architecture, and you can add after any kind of activation layer, dropout layer, or pooling layer. Frameworks as TensorFlow or PyTorch propose implementation of Siamese network without any problem, and you can reuse a lot of different ones which have been designed previously. This is our own that we have called the papyrus.net. It has been the first model that we have designed. It is very, very simple one. We have only 3 convolutional layers, and they share their weight. It is noticed here that each time you share the weights between the two branches. At the end, you compute some differences to compute the distance between the two branches, between the two inputs. In fact, you have two dense layers and you have the final result from softmax function. Before to run the Siamese network, we have to prepare the data. We have database, that's true. And the first one that we have used is a Michigan database with several thousands of papyrus fragments. But we have two difficulties to solve. First, in each image, we have several fragments, so we need to isolate each fragment in only one picture. But more important is that most often we have several thousands of fragments, but we have only 2 or 3, 4, 5, but no more fragments which are considered as coming together in one papyrus. So you have a lot of pairs which are not at all okay, which are not, which does not belong to the same papyrus, and we have only a small number of fragments which belong to the same papyrus. So to create more pairs of similar pairs, we have decided to create patch. So from each fragment, we extract a patch, square patches, and with same size, and we have selected those one who have writings or not. In fact, we have classified the patch. We have classified the patch with text and without text. We also have a rules that to ignore patches with too many background pixels because we can't return it. The advantage of this patch working is that as each patch is a square patch, we don't take into account any information, not all, but a lot of, we ignore a lot of information about the shape. We don't want to take into account the shape of the fragment. Why? It is a different question than the pulse. Why we want to do that? It's because, as you have seen before, papyrus is a kind of tissue, and it can be unraveled, and it can be, you can also have some missing piece. You can lose a very, very small piece and create a wool. We don't want to run an algorithm which try to adjust the shape. We prefer to focus on the different features that characterize texture and writing way, color of the ink, and something like that. I have not told before, but all the papyrus are not in the same language. It seems to us that we have tested a lot of different data sets, and we are not really sensible to the language, and we have obtained the same performance if we are in Greek, in Demotic, in Arabic language. It is an example of what we are doing to prepare the data before running. So you can see the example of in one papyrus, we have 2 fragments. And so we consider that whole patches coming from any of these fragments are corresponding pairs that match because they come from the same papyrus. And of course, patches coming from another papyrus are not considered as pairs that can match. Sorry. The trainings that the data set that we have created to run our network we have selected 500 fragments in different language. We have extracted to 12,000 patches, and as usual, we have split for training, validation, and test step. You can see here some sample of the patch that we can extract. Of course, the size of the patch has to be considered because if we have too small patches, we can't capture letter, for example, or symbol. So having a too small patch could cause some problems. To publish our result, we have compared the performance of PapyrusNet to another algorithm with the same purpose and the same database. It is the algorithm proposed by Koch in 2015. And we can see that independently, if we select patches without text, with text, or randomly, we are always better than the Koch algorithm. It is important to notice that as we test a lot of pairs, it is important to verify when we check the performance, if we have performance for the true positive or for the false positive. In fact, we have a lot of pairs that does not match. So you can obtain very good performance just by finding the pair which does not match. And so we have to take care of that. For a lot of tests and for this result also we have decided to balance the two sets. So we have reduced the number of pairs that does not match. If we go back to the puzzle problem, we have, in the previous step, we have created classes or a group of fragments that can be together, that can be considered as belonging to the same class. But it could be interesting to go back to the puzzle tasks, in fact, to try to obtain the position of the fragment. It is an hard task, and you see here some proposition made by Paumard and al. To solve the puzzle problem. But as you can see, with images that are very different from us because they have different colors, it could be an easy way to classify the different patch. But we have studied their solution and take some ideas. It is introduction of some hierarchical organization and proposition of position of the patch. In fact, the solutions that we have retained is the solution of creating a graph to try to find position for each patch. So, the idea comes from Lee and Lee, 2019, which proposed a Siamese network associated to a graph-based algorithm to find the position of the different pieces. Consider that the image reconstruction is an edge classification problem. Okay, so where the patches are nodes in a complete graph. How we are running this algorithm? When a pair of patches is considered close, the best place to assemble them could be analyzed. And so what we are doing, we extract 4 edge bands of each patch, and we try to consider the best place, up, down, left, and right, for to assemble with another one. Of course, when we took a decision to assemble 2 patches, we take into account this assembly to stick a new one. Example. So we did that with always with the same papyrus from the Michigan library. We have resized the image because they are too huge. In one image, we create 4 patches. We create patches that are not overlapped, and we extract band of for each patch. Okay. And so you can consider that in this, you have a patch here, you have another one, and you compute the probability or the distance, the similarity to be attached by right and left or by down and up. Okay. We have added also a 5th class to tell that no, we don't want to assemble this patch here with this one. Okay. This is the network, the Siamese network that we have used to do this work. That nothing really different. We have changed the number of dense layers. And in this part, we have the extraction of the band for each patch. And after that, we concatenate and we create this data are input that we give to the CNN. Okay. The output is a probability for each class. So we consider that one class is to be attached to the top, another one to the bottom, and the 2 other is left and right, and the last, no attachment. Okay. So what we have obtained with that? So we have obtained good result, 45% of accuracy for 200 images. We use the FN score for each one because it is considered when we have imbalance class and something like that, considered better than the current way to do accuracy. The hypothesis that we can assume when we display this result is that the features that we extract are related to gradient at the junction zone. And so it is easy to differentiate between high and low gradients between at the border of the patch. This is one result that we have obtained. This is the original fragments. We have cut in different patch. We have extracted the border of each one. We have computed the probability that 2 patches could be assembled by another one in this direction. And we display the values that we have obtained each time. This is another sample of what we did. You can see that here in the second, that he has not been able to put the 2 patches here inside the light one. And in the dark one, they disconnect the graph with the edge between nodes have been disconnected, and so it considers that this part is not connected to this one. I will show you that this display is conditioned by a threshold, and we will see the tool where we can change that. By default, the threshold is 0.8, if I remember well. And so it's why we have some disconnected part. If you down the threshold, you can obtain more edges. To use that, if we wanted to go back this kind of result to papyrologists, we absolutely need to provide some tool to visualize and to play with this kind of result. And so it is what we have tried to do. It is just a prototype. I would like to show you, the name is Viiograph. It is something, if I can switch my window, I have prepared everything. I hope that you can see it. Is it okay? Could you? Does my window change?
I can see a graph with
Great.
fragments.
Great. It is, perhaps it is not exactly. Okay. So here, so I have prepared a little bit before. You have the list of patches that you can load. Okay. Yes. You load the images and you ask to display. The tool does not compute nothing. You have to compute before. You put all the needed information in the right directory, and that just displays the results that you have computed before, and does not run any deep network and nothing. You have to do it before. It is just a very, very simple web interface with JavaScript and the Cytoscape library. And you can see that you can move your nodes. So you can, at this said that I have a hedge here, so probably I wanted to assemble like that. And this one could be assembled here. Okay. And this one here, I prefer here. If you wanted to see the result of your, I can try that. For example, you can suppress the 8, yes, and you can see directly with the image what you have proposed as assembly. Or you can go back to your previous step. So it is just a it is the first prototype and very, very simple tools, but just to play with the proposition of assembly, with the position about the position of the different patches inside one fragment. Of course, we absolutely need to at this step, we just work about some patch inside the fragment. We have to move to the fragment level, so to try to run it with the patch, with the fragment globally, and try to assemble in a papyrus. Okay, we have to do the two level. So at this time with Viiograph, because it is a graph computing and it requires some memory, huge memory. And so we have reduced to the problem to see if he is able to reconstruct, to reassemble, to redo the fragment from the different patches. And if you mixed two patches and you are able to compute the probability, two fragments, and you are able to compute the probability, it will compute the graph between these two fragments. But okay, something that we need to do more. Why I am not in full screen now? Sorry. Yes. Okay, it has been some photos that I took. If I have not been able to show you directly the tools. Everything is available in GitHub repository here of Cecilia, who did it and has presented this work to the Patrick workshop in ICPR this year. And we are, it is a work in work because we would like to propose to the papyrologist something more complete, to be able to work on ostraca, on papyrus, because the first experiment of Cecilia has been with ostraca, and now she has tried with papyrus and it works also. But we would like to have some tools that is able to work with different document and different type of algorithm or results, more than result. We never imagined that we can run directly on the web interface as deep learning computing, deep computing, because it is too costly. but it is a way to present results to papyrologists. Okay, so the last part of my talk is about what to do when you don't have enough data. You know that it is a main problem in deep learning, but more with all documents. What it means, we have a lot of data set, but what it is missing, it is a labeling, of course, as for everyone, and for everyone, a label, put some label on the document is costly, and time-consuming, difficult to reproduce because it is dependent of the person who did it. And more, we have the problem of availability of experts. It's not possible to ask to any person as Google did it to put some labels of this kind of documents, because they don't know how to do the difference between the Greek language and the Demotic language, that it is not so easy to do. So we have problems. So we can do as all the other person by using transfer learning, that a lot of another team has proven that it works sometimes. And the main principle of transfer learning is to train one time with big database and to reuse and retrain the previous models that you have obtained to escape to the random initialization of the network at the beginning, and to begin your training with some parameters values that have been extracted from the pre-training. So you can assume that in this case, perhaps if your own database is not so huge, it could work. We have tried, if we go back to the papyrus.net, we have tried, and we have testing different conformation, different configuration of Siamese network. One is our own, and more recently we have, because as you have seen, papyrus.net is a very classical convolutional neural network, and so we have tried to replace the three convolutional layer by VGG16 and by ResNet 50, and to compare their performance. So we have used ICPRS database, which have been built for a challenge in a conference, and it is not exactly a real database. It has been made especially for the challenge, but it is huge. And so we have reused it, we have used it to train, and we have tested directly the Michigan papyrus from these models that we have obtained from ICPRS, and you can see the result. In this case, ResNet is always the best. I will explain. It is a mean average. No, it is the result. Here we have tried to classify as we obtain distance between the two inputs. We have tested if the distance, the smallest distance, is correct, this top one. So the closest that we have discovered, is it the right one? Or does it belong to the list of the 10 first or to the 100 first? And it is the FN score of this result. We have fine-tuned. From ICPRS, we have used a part of the Michigan database to train again, and we have tested the same Michigan fragments. Now it is VGG16. It's the best one. But anyway, what we can conclude is in all times, we have better result than if we have no possibility to train, if we just reuse the training ICPRS to test Michigan. papyrus.net is not so bad. It is very simple and so less costly. but that's true that depending on the situation, VGG or ResNet are the best. But anyway, we need some ground truth. If we don't have, what we can try is something that we call self-supervised learning. It is something that we are doing at this time, is that self-supervised is a data set without any annotation. And so you create by yourself some annotation. So autoencoder could be a way to do that. Or what we are doing, we have considered that when we extract patch from the fragment, we create a kind of ground truth about that, and we reuse this information to enlarge the problem to the fragment level to constitute the papyrus. It is something that we are trying to do with the Geshem papyri, because in the Geshem we don't have any ground truth. Of course, it is in studying, so we have all the image, but the papyrologists are working on trying to find assembly, and they don't have at this time. So we have 260 papyri, and we extract from our result an ordered list of the fragments that could be assembled together from extracting features and distance that have been computed by applying the patch level at the fragment level to train the network. It is in work. This work has been submitted, and we are waiting for the result in 1 month, if I remember well. Just to finish, to achieve, I see that it is a time. That could be surprising, but it is the same person. It is Cecilia Ostertag too. Her main topic is Beurton-Aimar analysis, and she's using the Siamese network, similar to this one that we have shown before, but it is for 3-dimension MRI, so there are some modifications. She used Siamese to compare 2 images of the same patient at 2 different times to see if the patient is in a stable state or if the disease has grown up or not. So, and it works well, not so bad. We also use, since it is a totally new project about an old Vietnamese language, that small number of persons are able to reread, because it is some kind of Chinese-like language, but not exactly. In fact, the Vietnamese people in the old time, we use a Chinese character, and they combine them in a special way to reproduce their own language. So it's not possible to read that with a Chinese tool. And the number of persons who are able to read that are very small. And we are working on creating some automatic recognition of the character that has some digital dictionary. And we have created a database with different text and their ground truth by automatic recognition of the character. And it is submitted also. Okay, to conclude, Siamese network are, in my mind, efficient tools for a lot of different applications. They compute metrics to compare 2 images. They are not so expensive in time and memory resources, and they can be some kind of first treatment to apply another one after, as we have seen with the graph network. The main point that I want to focus and I want to point out is that as we work pair by pair, we have a lot of negative pair, and you absolutely need to take care of how you compute loss or accuracy in this case, because you can obtain a very, very nice result, but only by finding all the negative pair and miss more than half part of the affirmative pair, of the positive pair. Okay. As we have tested, we have tried, I have not presented that, but I know that it exists a triplet loss tool. We have tried it, we have not exactly obtained good result, and at this time we prefer to balance directly the data set, not exactly, but to reduce the number of negative pair, even if we reduce the number of data that we take into account. We have not tested at this time the GAN, but it is in the plan. It is for the next. Thank you for your attention. Do you have any question?
Well, thank you very much, Marie. Very
I'm
interesting.
sorry there's some noise around me. I hope that it is not so bad for you.
Oh, I can hear you very well. Can you hear me?
Okay.
So, well, is there any question from the audience? I have many questions, Marie. This is really unusual type of research. It's very interesting, and it seems like something really important as well, because there is all this heritage, all these very delicate papers that preserve some things from the history of humankind. So I think it's a very relevant research. I'm really proud of your work and to listen and learn. And my questions, well, there are many questions, but I think I will try to do the most simple ones. And I assume all this is supervised learning. So I wonder, because you show the puzzle thing. So the puzzle, when I assemble a puzzle, I have a picture of the final result. So it's easier because I took the pieces and then I follow the final picture. But in this case, we lost the final picture. So the final papyrus, the original papyrus is not assembled, and nobody took a picture then. So we don't have the picture to put the pieces. So how can we get the correct labels? How can we know that we're going to assemble the right meaning of the words, and we're just not assembling some other words that appears in some other documents?
It is a huge work. In fact, in Michigan database, for example, they have some fragments that they declare that they are together at the same papyrus because archaeologists and papyrologists have read it. And they have concluded that it is okay to assemble these two fragments because it is the same text. In the human task, when you don't use deep learning and the ground truth come from the papyrologist, they read, and they just try to discover from the text where is the ground truth and which fragment can be assembled.
So it means that the output of these neural networks are images that actually an expert tried to read it and make sense of it, is it?
The output of our network is a distance between two fragments. So after that, it's why we can produce an ordered list of the different fragments that we want to test. For the Geisham, we have at this time, we have for the 260 fragments, 70, we have the ordered list for each fragment, which one is the closest. And you can consider the 10 first, the 100 first, it depends. And after that, it is the task of the papyrologist to, it is a kind of just to create some groups, some classes of fragments, and hope that they belong to the same papyrus. And in fact, the first observation of the papyrus is very recent. It is 2 weeks ago. They said that, you know, that when they open the funeral mask and they create the cartonnage, in fact, they open a box and they put everything inside. And some fragments that are most often the 21st that are closest in the distance considering, they belong to the same box. So, and what they have seen that sometimes when there are some foreigners in the list, they mainly come from another box. So perhaps you could consider that the two cartonnages have been made in the same office, and they have reused the same papyrus when they create the mummies. They cut in the same original papyrus, and perhaps it's a good idea to put together these two boxes.
What a wonderful research. We have
it's exciting.
Yes, we have some questions from in the chat. Sahari Rosas, she's asking the following: is there something GANs can do that to replace the Siamese networks, or do they share similar objectives?
Yeah, it's something that we are studying. We have begun to study. We have no result at this time, but we know that it is something that we have to test and to try also to see if they can if we can obtain better result or not. We don't know.
Great.
In fact, in the story we have begun with the MRI brain images, and after that we have reused for another project, and it works.
Excellent. So very clever question of Sarahi. She identified that this can be also future work. Is still in plain development. What you do. Well, nice to see your presentation and your work, and so it was very interesting. Thank you.
Many thanks.